Hello, in this video we're going to talk about batteries, specifically Lipo or lithium polymer batteries like these ones here, and we'll find out why they've got all these funny plugs on them there. But we'll start off by looking at just batteries in general, how do they work, and we want to cover the fundamentals before we go ahead because it's good to understand how everything works, especially when you're dealing with something like this because, like I said earlier, these are not just any old battery, they are very high performance batteries. They contain a lot of energy and they perform very well, but you have to respect them, you have to look after them properly. They are a little bit fragile, they can be easily damaged by crashes and puncturing, overcharging, over-discharging, overheating, all kinds of things. Unfortunately, there is a lot to learn, and it's beginning to look like this might have to be a two-part video, or split into two separate parts. But we'll see how it goes. So let's have a look at how a really primitive, simple battery cell works. On the left here I have a little piece of copper, and on the right I have a little piece of zinc. You don't need to use a special piece of copper like this, you can use just a piece of copper wire. And for the zinc, if you find a galvanized nail, they actually have zinc on the outside, so you can use a nail and just some copper wire to do this. And you don't actually need copper and zinc, you can use lead and aluminium and a variety of other metals as well, but the important thing is that they need to be different. So over here I have a little bit of vinegar in this ice cube tray, and again you don't need to use vinegar, any acid apparently will work, some will work better than others. Apparently lemon juice is really good for this too. And these two electrodes, I'm going to call these electrodes now, they are connected to my voltmeter so that we can measure the difference in voltage between this point and this point. Now when I put these into the acid, so that they are both inside the acid but not touching each other, we should see that we read a voltage. In this case it's a little under 1 volt, and I've found that it will go up and down a little bit, and it sort of steadies out at about 0.93, 0.94, somewhere around there. Let's take a closer look at the zinc electrode that's been running for a while, and we'll see a couple of reasons why we don't use these zinc copper chemistry batteries in daily use very often, because they're not really that good. And as you can see, there are a bunch of bubbles showing up there. I think this is hydrogen that's being given off, and we don't really want bubbles of hydrogen coming out of our batteries. And another feature that we'll see when I lift this out of the water is that it's starting to build up. I think this is copper oxide, so this is actually coming across from the copper electrode, and it's forming a sort of a layer on here that inhibits the chemical reaction, so it's going to get less and less effective as this builds up. And I think it's pretty easy to clean off, but yeah, obviously you don't want to have to go and clean your batteries all the time. So one way or another, either this zinc is going to corrode completely and it'll just disappear, or it's going to get this build-up that makes it less and less effective. So at the end of the day, these batteries are not going to be very practical. Now, the voltage difference that the cell produces will depend on the chemistry of the cell. In this case, it's what kind of metals we're using. And I've taken the zinc out here, and we'll see, I have a little piece of aluminium, so just for the sake of it, since I've got this all set up for us to look at, we'll see what kind of voltage difference we get between copper and aluminium. This was about 0.5 before, and it seems to have deteriorated a little bit while I was organizing. Interesting. Anyway, it's a lot less than what we got with zinc, which is why I went with zinc to begin with. And we might as well also try zinc and aluminium and see what that gives us. Probably not that much. Okay, so that gives us actually a higher potential, and you'll notice it says 0 now because we've got the voltage terminals on the opposite way, so the electron flow will be going in the opposite direction to what we had before. It just means that now the zinc has become the negative terminal of the battery cell instead of the aluminium. I was curious to see what stainless steel would do. I have this ruler here which is made of stainless steel, and it actually gives us a pretty high potential difference there, 1.2 volts or 1. Wow, it starts off high and then it quickly drops down a bit, doesn't it? Copper and stainless steel. Oh, not much zinc and solder gives us about 0.55 volt potential difference. Solder and copper gives us about 0.4 volts potential difference. The solder is 60% tin and 40% lead. Anyway, from those examples you can see that the voltage potential of a cell is limited by the chemistry of that cell, or the metals that are used on the electrodes. So if you want to make the voltage of a cell higher, you're going to have to look around for some different metals than these common ones that we have here. And in particular, I think lithium is pretty good at generating a high potential difference in a cell. This is a table that I came across that shows you the various electrical potentials of some metals when they're used as the cathode or the negative terminal of the battery. So you can actually calculate this beforehand instead of fumbling around poking things into little dishes of acid like I was doing. And we can see here that the zinc, when it's used as a negative terminal, which is what we were doing, is minus 0.76 volts, and copper will be positive 0.34. But since one of them is going to be reversed, we can get the overall voltage by adding, say, we'll add this to the negative of that, which will give us 1.1. So I guess that means that in a perfect cell, copper zinc cell, we should have got 1.1 volts, but obviously my little thing was not perfectly constructed, so we only got 0.95 or so. But anyway, what I really wanted to show you here was, if we look right at the top, we'll see lithium, which all by itself can manage to do over 3 volts in perfect situation. The other way you can raise the voltage is by using multiple cells and connecting them all in a row, or in series, as we say, one after another. And that's what I'm going to do here. So I have a little piece of copper again, and this is soldered to a piece of zinc like that, and I've just split them apart so that they're going to bridge across the ice cube trays, and I have 4 of them now with acetic acid or vinegar in them. And when I plot this one down, we should have what we had there before, 0.95-ish volts multiplied by 4, and if I get this the right way around, that is a little bit under 4 volts. And yeah, so that's basically how it works. Cells in series will increase the voltage. And now that we have a little bit more voltage, we can start to actually do something with it. In this case, I'm just going to light up some LEDs. I've got 3 LEDs on there, and when we plug in my battery connection here, whoops, we can see those light up, and actually light up pretty well. Wonder how long this would run for. Probably quite a while, because these little LEDs only use a tiny little bit of current. So in case it wasn't obvious already, what we've made here could be called a 4-cell battery, because it includes 4 separate cells. And when we make it into one battery like that, these cells, they don't go away, they're still there. Each individual cell is playing its part. And when we're using these high-powered lithium polymer batteries that we use in our quadcopters, we have to be very aware of the fact that even though we're treating it as one battery, there are 4, in this case, 4 individual cells inside here, and we have to look after each cell individually quite carefully to make sure that we don't damage it. And just as a demonstration, so on the outside terminals of this, we can see the overall voltage of the battery as a whole is about 3.7, but if I take voltage from the intermediate points, we can see that, for example, this cell is 0.96 and this one is 0.89, so they're slightly different, and they're each individuals. That's the point I'm trying to make here. So in order to look inside this pack of cells and see what each individual cell is doing, how healthy it is and what voltage level it is, we have this cable here which is called commonly a balance plug or a balance lead or a balance connector or something. And we can see that in the case of a 4-cell battery, this one actually has 5 terminals. So even if it's not marked on the battery very well what it is, in this case it is marked, but it's not marked very well. You can see this tiny little dot in the 4-cell circle there. Even if it's not marked on the battery, you'll be able to see by the number of terminals minus 1 is going to be the number of cells in the battery. So in this case 5 minus 1 is 4. And why do we need 5 when there's actually 4 cells? Well, if we look back over here again, we have from the top to the bottom is there, that's 2 terminals, and then we have 3 because we need 1 terminal in between each cell, so that's a total of 5 terminals there. And we can use this to charge each cell individually and check its voltage and just make sure everything is okay. So this balance plug just lets us look inside this pack at each separate cell without having to open it up and connect a connector onto here somewhere. It just lets us, it's an easy access port, I guess you could say. And then this one over here with the large wires, hopefully if you're smart you will have figured out that this having just 2 terminals is simply the outermost 2 terminals, and when we're actually flying the quadcopter or driving the radio control car or whatever we do with this Lipo, this is where the bulk of the power is going to be coming out through all of the cells all together, and that's why it has a much thicker wire on here, because the balance plug, the small wires here, are mainly just used for checking voltages and topping it up when you're charging and so on. But when you're actually running, you want to have a bigger set of pipes like this for that current to flow through. For those who might be curious, this is what a single cell from a Lipo pack like this looks like if you break it open and take it apart. And you can see it's sort of a foil packed pouch thing, and they're actually fairly soft. I could probably bend this. I'm not going to bend it to show you, but it's soft enough to bend. And I've put some electrical tape over the terminals here because unlike my dinky little vinegar battery, if these terminals touch together that would be bad. So speaking of which, let's do a little voltage check and see what the voltage is in this cell. I think this is a good one. Yeah, so we're getting over 3.8 volts. This is just a storage charge, and that is way better than our copper zinc chemistry. Oh hey, and while I'm at it, why don't I also poke around with my voltmeter on the balance lead here and see what this shows us. So if I put my voltmeter on 2 adjacent terminals in the balance lead, we should see again about 3.8 volts for the first cell. If I shift them over one, we can check the next cell, 3.79. So we can check all of the cells individually like this, and they all look okay. Now if I put the voltmeter terminals on the very end terminals, we'll see the voltage of the whole battery. So it's 15.17. And if I check the voltage here, that's also going to be the same thing. So we should see 15.17 on there as well. So technically, yes, the first and the last cables on the balance lead are exactly the same as these two here. So if you're running a low power application, you could actually run it off the balance lead. But as I said before, we're not running low power things, we're running high power things. So that's why we have to have this specific lead here to actually run the quadcopter. Here's another important thing we can demonstrate by using this simple battery. I have my multimeter connected to the positive and negative terminals of the battery, so we're looking at all of the cells together here, and we've got about 3.7 volts. This is what we call the voltage at rest. So the battery's not doing any work, nothing connected to it, so it's just relaxing, and this is the voltage we have at that situation. But if we connect a load to the battery, in other words, we make it get off its ass and do something useful, in this case lighting some LEDs, we'll see that this load has caused the voltage to sag down to 1.7 or so in this case. And this is normal. The amount of sag will depend on how big the battery is and how big the load is. I like to think of this a little bit like a spring, because when you take the load off, it will sort of recover to around about where it was before, slowly. And this is sort of, in my mind, I like to visualize this like a spring. If you're not putting any load on the spring will stretch out like this. As soon as you squash it down, it will squash down to a certain point until it sort of equalizes with its force pushing up on that load, and that's the voltage that we saw before. So a strong, healthy battery is like a strong spring. When you put lots of load on it, it's not going to squash down very much. But a weak battery is like a weak spring, or an old battery that you haven't looked after very well, or it's had lots of charges through it, so the chemistry is starting to deteriorate. That's a little bit more like a weak spring. So when you push down on the weak spring, you'll be able to get that voltage to sag down a lot. Here's a real-world example of that situation using a lithium polymer battery on a quadcopter. Keep an eye on the number in the bottom left. That's the voltage of the battery. It's at rest at the moment, but almost immediately as we take off, we drop quite a lot of voltage there, and you'll see in the next few seconds it even hits about 15.7. So it's down from 16.7. We've lost a volt. At least it looks like that, but it's not really that we've lost a volt. It's normal for it to be sagging down a little bit like that. Here's a graph showing the typical shape of the discharge curve of a LiPo battery. So you can see at the beginning it does drop quite suddenly down from its at-rest value, and it will settle into a value that's pretty constant throughout the lifespan of the charge, and then it drops off right at the end quite suddenly. So right here you've got to stop using the battery at this point, otherwise you're going to be damaging it. Now this particular curve, I just sort of quickly fished this out from my Google search. It showed up in one of my first searches for LiPo discharge curve, and I noticed that there's some pretty heavy loads on here. So 175 amps is pretty high, so that's why it's dropping down quite significantly here. But the overall shape of this curve should be quite similar. If we look at that video that I just showed you before, my battery dropped down to 15.7 volts. So that's, if we divide that by 4, that's going to be something more like about 3.9 volts. So my curve would be more like about here. But the important thing that I'm trying to point out is that the voltage doesn't just go down in a straight line like this from beginning to end. It's normal for you to see it sag and then settle at sort of a more middle voltage while it's running. Now before I pack all this stuff away, I thought I might also take a look at using cells in parallel. This is not something that we see very commonly in LiPo batteries for reasons that will become obvious in a minute, but we'll just look at it anyway since we've got this already. So if you recall from earlier, we had cells going in series, meaning one after the other, and there was only one path for the electricity to get from one side of the battery to the other, and in my case it was going like this, and there. And parallel is the opposite of that, in that you do actually have more than one path for the electricity to flow through, and I have my zinc electrodes over here. I'm going to have 2 of them, and 2 of them on the copper side there. And when I put these into the electrolyte, now there are 2 paths for the electricity to go through. It can go through this way or that way. And we see that we don't actually get any increase in voltage. We have about the same voltage that we had before. So you may be thinking, well, what's the point of that? Well, the extra surface area of these double electrodes gives us more capacity to push current through. So we can get twice as much current through this set of cells now as we could before. Makes sense, really. Going back to the water analogy for a moment, I like to think of this as putting 2 tanks of water side by side, and they're connected like this so that the water can come out of both of them at the same time. But it's the same height as we had before, so we don't get any increase in voltage. We only get an increase in the overall current that can be delivered at any one time. And just in case it wasn't obvious, putting cells in series is a little bit like stacking the water on top of itself like that. So we get more pressure and more voltage, but it doesn't change the current that the battery is capable of delivering. But you may be thinking, well, if it's just surface area, why don't we just have one cell and take out this barrier in the middle so that it's just one little bucket of electrolyte, and just keep these electrodes with that surface area? Wouldn't that work as well? And if you were thinking that, well, yes, you are perfectly correct. And that is the reason that we don't see this very often in LiPo batteries. We can just make each cell larger. So as an example here, I'll look at this battery here, and we see that this one is marked with 3S. So S, if I haven't already mentioned this, maybe I didn't, but 3S, the S there stands for series. So there are 3 cells in series, and that's going to give us a total of nominal 11.1 volts for a LiPo battery. But not all batteries mark that they're in series, because it's just so obvious that it's going to be series that they don't even mention it. So if we look at this other battery here, we'll see it doesn't say anything about 3S, but it says voltage and then 3 cells. So there's 3 cells, and we just take it for granted that they are in series because, like we just discovered, there's not much point putting them in parallel because we can just make it bigger. So here's another battery. Everything about the battery below is the same except that it's larger. So you could think of having some smaller cells in parallel inside this one. We get the same voltage, but we get more capacity, and we can push more current out of the battery at the bottom at the same voltage. Hopefully that all makes sense, but that's why we don't see parallel in these LiPo batteries very much. At least we don't see it very much when we're using the LiPos, but it does come in very handy to be able to charge the batteries in parallel, and I'll look into this a little bit more in detail later too, but you can get something like this, which is called a parallel charging board, and this one lets you place 6 batteries in parallel, so all of the cells are going to be in parallel for the batteries when you connect them to here. You can see 6 sets of possible LiPo balance plug connections here. Sorry, it's not in focus, is it? There we go. But anyway, so it's not completely pointless to have parallel sometimes. So we'll look at this later on. Here's a really huge LiPo battery that I found on Hobby King. This one is a 6S, so there are 6 cells in series. I should have mentioned this notation earlier, but the notation will be 6S something P, and I thought I'd show you this one because this one does actually have cells in parallel. If we look at the configuration, it's got 6S2P, so the 2P stands for 2 cells in parallel, so it's kind of the same as what we just saw in the little vinegar thingy. But more often than not, you'll find that there's no P mentioned in the notation here, so it'll just be 6S or 4S or whatever, and we'll take it for granted that it's just a 1P cell. So if you were paying attention, you should be able to tell me what the notation would be for this cell that I'm just about to connect up. And notice I have a bridge in between those there. And actually when I put this in, it kind of gives away half of the answer. But anyway, you should be able to tell what the configuration of that battery is. Well, I think I'm going to break this video here. It's starting to get a little bit long. There is still a lot more to cover though. For instance, we didn't really talk too much about LiPos specifically, including one very important feature of them, which is that they are rechargeable. So we also have to talk a little bit about charging and how that's done. And we'll also have to look at something called the C rating of a battery, which is fairly important as well, and probably a few other things too. But anyway, this is where this video is going to finish, so I'll thank you for watching, and I'll see you in the next one.